example where a semaphore is used to coordinate the activities between two tasks in an embedded system for controlling the time. So here you can see the task update time task, which is responsible for updating the time based on an interrupt. And there is another task, a read time task, which is used to read the time from the time device. So the update time task will be updating the time device based on interrupts, and after the time is updated, this information has to be passed to the read time task so that the read time task can read the time device and send that time to another task or to a display device. So in this case, a semaphore can be used to coordinate or synchronize the activities between these two tasks. The updated time task before updating the time will depend on a semaphore. So the semaphore in this case is sUpdateT. So this sUpdateT semaphore is taken by the update time task before making the changes in the timer device. The timer device is a shared resource which is shared between this task and the other task. So in this case, before updating the time, the update time task will depend on the semaphore sUpdateT. So once it gets a semaphore, it will write the changes. It will write the new time value as well as the date of the time device. So time device is a shared resource in this case. So once the changes has been made, it will release a semaphore. So in this case, it will use the function OSMPOST to release a semaphore. So if the semaphore is available, its value will be 1. So the update time task, which is running a function OSMPend to get the semaphore, will get the semaphore if sUpdateT value is 1. So once this semaphore is taken by update time task, its value is changed to 0, so that the other task, when it tries to get the semaphore, it will not get the semaphore. It will get the semaphore only when the semaphore is being released. So after making the changes in the timer device, the update time task will release the semaphore sUpdateT, so that the sUpdateT value is changed to 1, so that the next task can take the semaphore. The second task, which is the read time task, is also sharing the same timer device, which is shared by the update time task. So the update time task, once it has made the changes in the timer device and releases the semaphore, this task, that is read time task, can get the semaphore. So it is waiting for the semaphore sUpdateT. So once this sUpdateT is being released by the update time task, the read time task can take it. So OSMPend sUpdateT, this function will depend on the semaphore sUpdateT until it is released by the update time task. So once the update time task releases the sUpdateT semaphore, the read time task will get the semaphore and it can do the operations with the time values. And once it has completed its operations, it can release the semaphore using the function OSMPOST sUpdateT, so that the sUpdateT is again changed to 1. Its value is changed to 1 from 0. Once this semaphore is taken by a particular task, like a read time task, sUpdateT value is changed to 0 from 1. It will get the semaphore once it is available. That time sUpdateT value will be 1. Now, when this task has taken the semaphore, the sUpdateT value is changed to 0, so that the other task will not get the semaphore once it is being used by a particular task. And once it completes its operation, it can release the semaphore. So once a task releases the semaphore, its value is changed again to 1, so that the other task can take the semaphore and do its operations. So let us understand what is meant by mutex. When a binary semaphore is used at the beginning and end of critical sections in 2 or more tasks, such that at an instance only one section of the code can run, then the semaphore is called mutex. So what is meant by critical sections of a task? Critical sections of a task are those sections which should not be interrupted during the execution of a program. So during the execution of critical sections, interrupt should not happen. So how it is implemented? It can be implemented with the help of semaphore. So before entering to the critical section, a task can take a semaphore, so that it can ensure that no other task will interrupt the execution of these critical sections, because it has already taken the semaphore. So in between, if another task tries to execute, it will try to take the semaphore, but it will not get the semaphore because this task, which is executing the critical section of the program, is already taken the semaphore. So in this way, critical sections of the program can be executed without interrupts with the help of semaphores. So if you use semaphores for this kind of applications, then the semaphore is called a mutex. This mutex is derived from, the word mutex is derived from the word mutually exclusive. In the previous example, we have seen two tasks, task update time and task read time. So these two tasks are using or are sharing the same timer device. Both are operating on the timer device. The update time task will update the date and time to the timer device, whereas read time task will read date and time from the timer device. So in this case, we need to ensure that at a time only one task is going to operate on the timer device. So a semaphore can be used, as discussed in the previous example, to control the sharing of the resource between these two tasks. The timer device is shared between these two tasks. So semaphore used in this way is called a mutex. Multiple semaphores can be used for synchronizing the tasks in an application. So in this figure, we can see 5 tasks where task I, task J and task M share a common semaphore X, whereas the other group, task J and task L, share another common semaphore Y. If multiple sections of a task code or task shares common resources or devices or files or variables, then a semaphore can be used to effectively manage it. How? A semaphore provides a mechanism to let a section of the task code or a task to wait until another section of the task or another task finishes the code, so that this particular task can use resource. So a common resource or a device or files or variables can be shared with the help of semaphores. When a semaphore is waiting in a task for a resource, then when the semaphore is given, that means it is posted, then that task code can use a resource. So the resource gets unlocked when the semaphore is given or when it is sent or posted. In this way, semaphores can be used as a resource key. The resource key is one that permits the use of resources like the CPU, the memory, or other functions or critical sections of codes. Now we have seen that a binary semaphore can be used as a mutex. That means a mutually exclusive semaphore, or it can be even used as event notifying flag. A semaphore can let one task among multiple tasks to run. That means that the task state can be changed into the ready state or running state when that semaphore is available for that particular task. In this example, let us analyze how multiple semaphores are used to control the execution of multiple tasks. Let us consider the tasks task I, J, K and L, whose execution are controlled with the help of multiple semaphores. Consider the semaphores S task 1, S task 2, S task 3 and S task 4. Initially, the semaphore S task 1 is having a value 1, whereas S task 2, S task 3 and S task 4 are 0. When task I went on the semaphore S task 1, it will get it because S task 1 is equal to 1 initially. So task I will execute, the course of task I will execute because the semaphore S task 1 is taken by task I, and once it finishes the execution, it will pose a semaphore as task 2. So we can see that the task J will be pending on as task 2. So when task J gets the semaphore as task 2, it can execute. Let us see that. Task J is pending on the semaphore as task 2. So this semaphore as task 2, when it is released by task I, task J can execute. The course of task J will be executing when as task 2, the semaphore as task 2 is available. When it is available, it will be available when task I releases as task 2. When the second task, task J, completes its execution, it will post the semaphore as task 3. So another task K may be waiting or pending on as task 3. So once task J completes the execution, it will post the semaphore as task 3 so that task K can, when the semaphore as task 4 is released by the task K, task L will get the semaphore. So we can see that task L is pending on the semaphore as task 4. So when task K has completed the execution, it will release the semaphore as task 4, which can be taken by the task L. It will execute. Now when task L has completed the execution, it will pause the semaphore as task 1 so that again task A can resume the execution. So in this example, we can see that when a task A is to start running, it takes a semaphore as task 3. The OS blocks the tasks I, J, and L when K executes or when K runs. The task L waits for the release of the semaphore by K. Let us analyze a situation where a number of tasks are waiting for the same semaphore, but it means multiple tasks are pending on the same semaphore. So which task has to get the semaphore? It can be configured in multiple ways. One solution is the task which is waiting for the longest time. It means the task which has first place a request for the semaphore can be given this semaphore. Another option is like task can be prioritized. So a higher priority task can be given the semaphore while the lower priority tasks will wait for the semaphore.